And we should remember that, oh, it's just a note, we've kind of assumed that our objects are point masses, and we will continue to assume that our objects are point masses until we do rotational stuff. But for gravitation, it needs to be a point mass that is at the center of mass of the object. That's what you're treating it like. So the r in the formula is the distance from the center of mass to center of mass of the two objects. So even if you have, even if my two fists are pressing up against each other, like, that doesn't mean the distance is 0, because it's not actually 0. It's always to the center of mass, so you can never get 0 distance between two objects. And even when you press up against, like, there's a small distance between my palms. It's always distance between things. Yeah. But actually, it's a calculus problem. Like if you're standing on the surface of the Earth here, not to scale, what you actually would do to be totally accurate is integrate up the gravitational force from this and 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 this, and all the gravitational force from these infinitesimally small particles all the way through the mass. But for our purposes, Earth and other planets will be uniform spheres, because you don't have calculus to deal with anything more complicated than that at the present time. Right. But we must also remember that force is a vector, so things can happen at angles. So we've got a mass m at the origin. We've got 3m at 4L, 0. Oops. And we've got 2m at 0, 3L. Yep. When you're reading these problems, make sure you read the coordinates carefully. There's always somebody who on a quiz or test draws this when they're actually 3 in a line, or vice versa. They're 3 in a line and they draw this because they're not carefully reading the ordered pairs. So don't do that. I will be sad, and you will be sad also. Right. So we need to do vector stuff. So mass 2m, how many forces are acting on 2m? 2. One from m, one from 3m. All right. The force from m is in what direction? Right, which is the negative y direction. So we have 0, negative something. And that would be g times, what do we have? 2m times m. So that's going to be a 2m squared over 3L squared. Yes. That's the force from m. The simpler one. 3m exerts a force at an angle. Okay. When you're doing something like this, so in principle, this is the concept of what you're doing is no more difficult than any other force vector problem we've done. But there are a lot of things with powers of 10 and stuff to multiply together. Not in this problem because it's variables, but I think maybe the easiest way to write it out is to write out your magnitude out front and then multiply by a vector thing. So the magnitude would be, what do we have? 2m, 3m, over what's the distance between them? 5L. 5L. Oh, I'm so nice, aren't I? Give you a nice 3, 4, 5 triangle. Times, okay, and what direction is that? X direction is positive or negative? And the y direction is positive or negative? negative. And what angle are we looking at in this triangle? Or what angle do we want to look at, I guess? This one? Okay, if we're doing that one, we can't do cosine for the x component. Cosine we get to the y component. So, but the handy thing here is that we have the sides of our triangle, so we don't actually need to find the value of the angle. We can just put in the ratios, right? So the x component of this will be the sine of this angle, which is 4 over 5. And the y component will be the cosine of that angle, which is 3 over 5. These could look more complicated. But keep in mind that the denominator here will be the square root of the denominator here. So this is 5L squared, and this is, if we didn't have variables, like it's 4L over 5L. So this denominator is 5L, this is 5L squared, right? So if you have numbers for everything, what's down in the denominator here will be the same, like this will be something squared and this will be something to the first power, or this will be like just something and this will be the square root of that something. So you can multiply them together into one thing to the 3 halves a lot of times. Anyway. And then we got to do fraction multiplication. For our y coordinate, we've got 2 times 3 times 4. What's 2 times 3 times 4? 24 m squared over 5 squared times 5, 125 L squared. This is 4L over 5L, so those go with bye-bye. And then for our x, or for our y coordinate, what do we have? 2 times 3 times 3? What's 2 times 3 times 3? We got a negative up front. Is Taehyun the only one that knows how to multiply? 18n squared. And what's our denominator, Yoonjung? 125 squared. Right. So then we add them together. And the x component's already done because one of them's 0. Well, actually, it might be nicer. It might look a little bit nicer if I pull out the gn squared over L squared. And what do we have here? 2 over 9. So we've got 2 over 9 minus 18 over 125. Frac. That's nice. 88 over 1125. And then we need to find magnitude and direction. So the magnitude is square root of 24 over 125 squared plus 88 over 1125 squared, which doesn't make a nice fraction, I guess. 0.207. And the angle, we can actually get an angle because, what? Oh, I didn't store those, whoops. I knew that was wrong because it was negative, and this is in quadrant 1. About 22 degrees above the positive x-axis. All right. Yay. Now, if these were numbers, it is difficult to punch into your calculator because there are a lot of numbers with powers of 10 that you're multiplying and then adding. So be careful. recollect, what does free fall mean? It means that gravity is the only force acting. That's the definition of free fall in physics land. And if gravity is the only force acting, then we can say gravitational force equals ma, right? So then, Newton's law of gravitation, sometimes it's written, or oftentimes, instead of writing m1, m2, it's written little m, big M, where big M is like the planet or star or whatever, the big object, and little m is the little object. And these two m's are the same thing, so you get acceleration equal to gm over r squared. And if you plug in the mass of Earth and the radius of Earth, what do you get? 9.8, right. So if you take g times mass of Earth over radius of Earth squared, you get about 9.8 meters per second squared. So that's where little g came from, as long as we're close to the surface of the Earth. As long as that distance from the center of the Earth is not appreciably different from 6.37 times 10 to the 6th. And that is times 10 to the 6th, so you really need to get like pretty high, like at least a 10 to the 5th away for that to change your gravitational force. 10 to the 5th being, what, 100 kilometers above the surface of the Earth? Yeah. So, the gravitational acceleration at any point, and I wrote g here, but that's not good. I should write acceleration subscript g, gravitational acceleration, because little g is 9.8 meters per second squared. Nowadays, this is called the gravitational field. At the present moment in time, scientists conceive of forces as being carried by fields. So if they're, stick a mass out in space, and it generates a gravitational field, which then, if you put an object in it, then it responds to that gravitational field by having a force exerted on it. So, as you can see, if you take this gravitational field times the mass, then you get gravitational force. Okay. There's electric field, magnetic field, like every force has a field. Every fundamental force. So, if you put an object there at a point, it will accelerate at a rate equal to gm over r squared. But the field exists even if there isn't a second object. At least that's how the present conception goes. The concept of a gravitational field is very abstract, and it's like it's hard to visualize. Although you've probably seen the diagrams where of a sheet, you put a mass on it, weighs it down, so it bends this thing toward it, like space-time is bending or whatever. Anyway, yeah. So gravitational field. The gravitational field has units of meters per second squared because it is acceleration. I am telling you this, number one, because it's how physicists currently perceive the world, so that's worthwhile to know. And also because some questions, either in your book or on the AP exam, may use the term gravitational field, and you know what that means. Gravitational field, gravitational acceleration, essentially the same thing. Although, to have an acceleration, you need to have an object there.